what will explain I now, busbar protection and its important role in the power grid. So that's a little bit a warming up, both for me and also for you, about really the necessity of protection and busbar protection in especially, and also a little bit I will explain also some very basics of the basic definitions of busbar protection. Task of protection. The protection cannot prevent the short circuit. I guess you know it. Let's see this small video. What we have seen here is a so-called involving fault. So it started from busbar protection point of view as an external fault. We have seen a very strong arcing. And the busbar were on the top of this small video, and as soon as this external arcing has reached the busbar protection has immediately cleared the fault. So busbar protection cannot prevent the short circuit, but it can minimize the results of short circuits by protecting the equipment from overload and also from damage. Of course, very important to save human life. And how does it do? Protection protects human life and prevents damage from the equipment by tripping really selectively within milliseconds to maintain also the network stability. That was for protection in general. Why do we need busbar protection? A busbar is really a point of convergence of many circuits. It's a concentration of power and therefore really high and destructive fault currents can result. So you can see this in this very small single line diagram. Single busbar. We have several generators, we have several consumers like motors here in this case, and we have also transformers to a lower busbar voltage level. And so really here the busbar is a very high point of convergence, a high concentration of power. And therefore, that's the reason a busbar fault really endangers the stability of the whole grid. If a busbar fault could really not clear it in time very quickly, it could happen that really a whole station, the net will be unstable really for a whole country, for a whole continent like Europe, if we have a high destructive fault on a busbar which will be not cleared on time. So the general requirement to clear a busbar fault is 200 to 100 milliseconds, inclusive the circuit breaker operation. This sounds quite high, so that's a general requirement from the government, but typically for really high voltage, extremely high voltage busbar protection, the requirement from the utilities is that the device itself, without the delay time of the circuit breaker, is to clear the fault really sub-cycle. That means to detect the fault within one sub-cycle and at least to activate the binary outputs of the device itself. Also, we need a high degree of availability and dependability. And especially in very extreme high voltage level, in the meantime we have also more and more redundant busbar protection. That means a main 1 and a main 2 busbar protection system. And a busbar fault also, because it's very destructive, can lead to very, very serious damages of the switchgears and may also endanger human life. And therefore, once again, really a very fast and selective fault clearance by busbar protection is necessary. Reasons and probability of a busbar fault. What are the typical preventive measures? Typical preventive measures are single bolt metal enclosed switchgears, so-called GIS stations. And also with GIS stations, we have a division into separate compartments. This reduces a lot the probability of a short circuit in our busbar protection. And of course, state of the art, you typically have also a switchgear interlocking available in each substation. What are the reasons? The reasons are mainly mechanical problems, especially problems during the running time of the disconnectors, mechanical problems sometimes of the CDs, but mainly of the disconnectors, sometimes also mechanical problems of the circuit breaker. Not so much a problem in GIS stations, it's more a problem in air-isolated substations, is to have isolation problems. Pollution flashovers, we have seen this in our short video at the beginning. This was most likely an isolation problem. And I would say that's really the most likable reason for busbar protection faults are human errors. So typically the switch on the fault error. So maintenance activity, the cable or the busbar has been earthed by some cable. The maintenance activity should be removed, was finished, and somebody forgot really to remove the earthing cable and once again. And then we have a typically switch on the fault situation, which is the basic and human error. Okay, now maybe before I will give you the answer of your question, what is the average probability of a busbar fault? Average probability, of course, it's only a very rough average, is so typically one fault per 10 years to have a busbar fault. But if we have such a busbar fault, really the impacts can be really tremendous. We will see it later. And also maybe one additional remark, we have only one fault every 10 years for a busbar fault. But my former colleague, Matthias Schick, maybe some of you still know him, he said every time, but we have the highest probability of a fault per meter. So if you're thinking, okay, the busbars compared to really overheat lines for more than 100 kilometer, okay, the probability is higher, but the probability per meter, you have the highest in the busbar. Shortly before this warm-up, I will show you a very impressive video. I have taken this video by myself during some protection tests in an air-isolated switchgear in Austria. This air-isolated switchgear in Austria is now removed via a new GIS substation. And so this GIS substation will replace this air-isolated substation. And so this air-isolated substation it was possible to make very high destructive tests with this air-isolated substation because it will be replaced now by this new GIS substation. And what we see now is what happens if we have no dedicated busbar protection and we have only a backup protection, and in this case it was a distance protection in the reverse zone with a clearing time of 300 milliseconds only. In former times they had protected the busbar with a 7SS52, and I personally could block the 7SS52 so that we have the fault clearance time of about 300 milliseconds only. And let's see what happens if we have a high destructive busbar fault and a busbar protection without dedicated busbar protection. Okay, you could see it was like an atomic bomb. So you couldn't see anything for some seconds because your eyes they were completely flashed, and afterwards you could see on the substation, on the cable where this short circuit has been simulated and has been tested, it was completely carbonized. So this is really a very impressive video which shows really how necessary really a dedicated busbar protection is, and it's really in the high voltage really to make only a busbar protection with a backup protection of 300 milliseconds of the distance protection. It's really not state of the art. Come and let us explain a little bit really some fundamentals, some fundamental definitions. We need in busbar protection really a selective tripping, and really a selective tripping is really a basic demand of each multi-section busbar protection. This will come more in detail later. Just to repeat the most important definitions as much as possible. So selectivity in a busbar protection scheme is achieved by splitting the protection, the whole busbar, into independent zones. We call it measurement systems or measuring systems. And as it is a differential protection, the limits of the measuring systems are, as in every differential protection systems, are the current transformer. So really the area will be limited by the current transformer. And the disconnectors, we need disconnector positions in switchable busbars. It's different, of course, in a single busbar, but in a double busbar, triple busbar, we need really the disconnector image to assign the feeder currents to proper measurement systems. What elements do we need to configure busbar protection systems? We see here now a little bit more complicated busbar protection system. We are seeing here a triple busbar with also a transfer bus system and one coupler. So what do we need to configure a busbar protection system? We need to configure the busbars, shown here. So we see here all in all 6 busbars, 6 independent measurement systems, busbar sections. We need the busbar disconnectors. We need the busbar disconnectors here. You can see here also the busbar disconnectors. We need to configure the current transformers. It's also seen also with these red circles. And we need the circuit breakers. And if available, we have to configure also the sectionalizing disconnectors. And if available, also we have to configure the transfer bus disconnectors. Whereas optional only are the line disconnectors. So line disconnectors we need only in case we have a transfer bus. So here it's the case. In this case, as we have a transfer bus, we have to configure also the line disconnectors. And also we need the line disconnectors in case of parallel lines. Some further basic definition. What exactly is a centralized busbar protection, and in contradiction, what is a distributed busbar protection system? So let me read really first the definition. A centralized busbar protection, we speak about a centralized busbar protection if the main protection function in a busbar protection is of course a busbar differential protection, and the analog measurement current value acquisition of the current are in the same device. it's important to understand it doesn't matter really where's the binary signals, where's the disconnector position, where's the circuit breaker position, where's the trip command will be acquired or will be sent from. Really essential, important to speak about a centralized busbar protection is if the analog current measurement acquisition is in the same device. The distributed busbar protection. What is a distributed busbar protection? The main protection function, the busbar differential protection, and the analog measurement value acquisition of the current are located in different devices. And these different devices are typically located near to the process. So here in this shot, you will see a distributed busbar protection. The central unit will be this middle one here on the button, and the bay units or the merging units are located directly to the process, are connected to the primary current transformer. And in this case, we are speaking about a distributed busbar protection.
So thank you, Rainer, and good morning or good afternoon to everyone out there also from my side. The content of the next section is a short review to the ZProtect 4 solutions. I want to explain the possible solutions we offer with the ZProtect 5 portfolio and make a comparison of ZProtect 4 and ZProtect 5. Okay. This slide may be familiar to some of you who already have experience with the ZProtect 4 7SS52. For those who are new to this, I would like to tell you a little bit about it. The 7SS52 is a distributed busbar protection solution. This means the process signal, in example the current transformers, the circuit breaker, the disconnectors are connected to the bay unit. This is meant with the symbols on the bottom of the slide. The bay units are then connected to the 7SS522 central unit. So the 7SS522 is kind of the brain of the system, collecting and processing all the data from the bay units and doing the differential protection. The central unit in this case is based on the ZProtect 4 platform. The bay units are 7SS523 or 7SS525 devices, which are actually devices based on the ZProtect 3 platform. In this ZProtect 4 distributed approach, the bay units are connected via star connection to the central unit. The connection is done via multimode fiber optic cable. This is meant with the turquoise connection on the slide. The maximum distance between the bay units and the central units is 1.5 kilometers. The protocol for the communication between the bay units and the central units is the HDLC protocol. The measured value synchronization is done by the protocol and no additional time synchronization is needed in the setup. The 7SS52 busbar protection is applicable for big substations with single, double, triple or quadruple busbar systems with or without transfer bus with up to 48 bays and 12 busbar sections. In addition to the 7SS52 device, there are also other solutions in the ZProtect 3 or ZProtect 4 portfolio. In the ZProtect 3 portfolio, we had the 7SS60 device, which was a centralized busbar protection. This is the first device on the slide. Of course, the device is quite old, nothing we want to promote here. The ZProtect 4 solution for centralized busbar protection is the 7UT6. The 7UT6 is actually a transformer differential protection device, which can be used as well for busbar differential protection. This was necessary because before the ZProtect 5 7SS85, we had no other ZProtect 4 centralized busbar protection solution. The 7UT6 can be used for single busbars with up to 12 feeders without sectionalizer. The 7UT6 device are the ones in the middle of the slide. And of course, we have the 7SS52 in the ZProtect 4 portfolio. The 7SS52 is for complex multi-bus systems in a distributed setup. All these devices are either already discontinued in the product portfolio or already announced for product cancellation. The 7SS60 was cancelled in December 2019. The 7UT6 is announced for product cancellation in September 2024, and the 7SS52 is announced for product cancellation in March 2024. So it's time to think about a new solution with ZiproTech 5. The good news is the migration path to ZiproTech 5 is a quite easy one, because every device from the 7SS60 to the 7SS52 can all be replaced with the ZiproTech 5 7SS85. The migration path is displayed with these turquoise arrows on the slide. The 7SS85 can be used in a centralized approach or in a distributed setup. For the distributed solution as bay units, you can use every ZiproTech 5 protection device or, of course, the 6MU85 as merging unit in the feeder. So in ZiproTech 5, we have one platform, one device, and one configuration tool. The ZiproTech 5 7SS85 fits to all system configurations. You can realize the centralized configuration, where all the process signal and currents are connected directly to the central unit. You can realize a distributed configuration, where all the process signals are connected to merging units, and the merging units are connected via process bus to the central unit. Or you can realize a hybrid configuration, where some data is collected by merging units, and some of the process signals are directly wired to the 7SS85. So from the small switchgear, which is a compact design, in example a gas-insulated switchgear, to the large air-insulated system, which like 40 bays, triple busbar with transfer bus and up to 10 bus zones are possible with the 7SS85. One device for all configurations, but of course the solution themselves are different. For a centralized configuration, we use the 7SS85 centralized approach, quite obvious. For the distributed setup, you can use either the 7SS85CU distributed busbar protection or the 7SS85 IEC 61850 compliant solution. Oh, this was a bit too fast. The IEC 61850 compliant solution is fully integrated in the overall IEC 61850 process and station bus system architecture. It is a very flexible solution, but the engineering effort is quite high. The 7SS85CU distributed busbar protection solution is also a process bus solution based on the IEC 61850 protocol. There are flexible streams used, but with the fixed stream type IEC 61869-9. The sampling rate configuration is set to 4000 Hz and 1 ASDU. For the base, only proxy elements are available. The engineering is simplified following an automated process. It is additionally possible to configure user-defined goose messaging. With this solution, it is not possible to integrate third-party merging units. Okay, so in this case, the central unit is no longer the overall brain of the system. The bay units have some intelligence as well. You can maybe imagine it like this. With the 7SS85CU solution, the engineering effort is lower, and you can realize bigger busbar systems with more measuring points. For the hybrid setup, you must use the 7SS85 IEC 61850 compliance solution. Okay, now I want to dive a little bit deeper in each solution. This slide shows a single line diagram of a double busbar system with 20 bays. In this sketch, only 3 of them are drawn as an example. So typically for the centralized approach here, the signals of the base, that means the two disconnectors, the circuit breaker and the current transformer, are directly connected to the 7SS85. Of course, enough current inputs must be available in the device. So with up to 20 base, the device is a big one. In the 7SS85, there's a function group busbar with, in this case, 2 bus zones. Each bus bar is one zone in this example. If there's, for example, a sectionalizer in the bus bar, the number of bus zones is greater. In the function group busbar, the busbar protection algorithms are running. The check zone protection and of course the busbar differential protection algorithms. For each bay, there's a bay including all the elements that are physically actually there. So there are in this case a function group current transformer, 2 function group disconnector, a function group circuit breaker, and a function group voltage current 3-phase if additional backup protection functions are required. In the function group circuit breaker, some additional functionalities like the circuit breaker failure protection or end fault protection are included. The engineering process in Dixie 5 is to draw the single line diagram as it is shown here, create the 7SS85 with all these function groups and elements and functions you want to use, and then connect them to the elements in the single line editor. For the centralized busbar protection, the so-called significant features 9 and A to E are relevant. Rainer will explain later what the significant features are all about. And when I show you the device selection in the Cyprotec 5 configurator at the end, you will get a better understanding. With the 7SS85 centralized, up to 20 measuring points and 6 bus zones are possible. The 7SS85 centralized is a cost-optimized solution because you need only one device. You can learn more about the centralized solution in our 3rd tutorial next year. Okay, the next slide shows the basic principle of a distributed busbar protection using the IEC 61850 compliant solution. The single line diagram of the system is basically the same. With this solution, up to 24 bays are possible. So in this case, in the sketch, the last bay is called bay 24. We are here talking of a distributed system, which means the process signals of the circuit breaker, the disconnectors and the current transformers are connected to the merging unit and not directly connected to the 7SS85. The merging units are then connected by process bus to the central unit. In this case, here the communication topology is drawn like a star connection. We will talk about the possible communication topologies for distributed busbar protection systems in our 3rd session also next year. The device structure of the 7SS85 in Dixie looks mainly the same as for the centralized configuration. In the 7SS85, there is the same function group busbar with the 2 bus zones and the very same algorithms as check zone protection and busbar differential protection. Also in this setup, we have for each bay, a bay with its function groups disconnectors, 2 times, a circuit breaker, and a function group current transformer. Optionally, a function group 3-phase can be added if further backup protection functions are required. In a distributed system, it is also necessary to parameterize the merging unit. Just like for the base in the 7SS85, we need the same function groups. About the bay-related functions like circuit breaker failure protection, end fault protection, or backup over current protection, some of them can be configured in the merging units, some of them in the central unit. In this example, the end fault protection function is configured in the 7SS85 bay in the function group circuit breaker. For the end fault protection, this is the only possible solution. On the slide, the end fault protection 50EF is shown in the darker orange. The circuit breaker failure protection and the backup protection functions in the function group voltage current 3-phase can be configured in the merging units or in the central unit. They are drawn in a lighter orange on the slide. We recommend parameterizing all additional functionality mentioned before in the merging unit to keep the processor load in the 7S85 on a lower level. In addition to the device configuration in Dixie, it is also necessary to make the IEC 61850 communication configuration in the system configurator for this solution. A description of these necessary steps can be found in the manual, but a good understanding of process bus is required in this case. The engineering effort is significantly higher compared to the centralized approach. With this solution, up to 24 CTs and 6 bus zones are possible for a distributed setup. The 7SS85 is fully integrated in the overall IEC 61850 process, and it is possible to integrate IEC 61850 compliant merging units from other vendors. Okay, this slide shows a hybrid busbar protection system using the IEC 61850 compliance solution as well. Hybrid means in this case that you have merging units for some base in the field, and some of the process signals are directly connected to the 7SS85. This hybrid setup is only possible with the IEC 61850 compliance solution. In this sketch, Bay 1 and Bay 2 are connected to merging units, and Bay 20 is connected directly to the 7SS85. For the hybrid setup, only up to 20 measuring points are possible. The configuration in Dixie is mainly the same as for the fully distributed IEC 61850 compliance solution. The only difference here is for the bay that is directly connected, you must put all the functionality to the bay in the 7S85, just like in the centralized approach. The relevant significant features are the same as for the centralized approach and for the fully distributed IEC 61850 compliance solution. This slide now shows the 7SS85CU solution. This is a distributed solution for up to 48 bays. The difference between the centralized solution and the 7SS85CU distributed busbar protection is fundamental. For the centralized and the IEC 61850 compliance solution, you need to create all elements for the busbar differential protection and also nearly all the functionality for the base in the 7SS85. The single line elements of the base must be connected to the 7SS85 as well. In contrast to the 7SS85CU solution, really lives up to its name, distributed busbar protection. Here you put all functionality like breaker failure protection, end fault protection, backup protection function in the merging units. You connect the graphical elements in the single line to its representatives in the merging unit. After completing the engineering of the merging units, you must update the central unit in the single line configuration. During this update operation, the system configuration created in the single line editor is also created in the 7SS85CU using the representations of the connected base, circuit breakers, disconnectors and measuring points. During this process, all necessary elements are automatically created in the 7SS85CU. These elements are visible in the project tree of the 7SS85CU and in the information routing. For the base, only bay proxies are created. They only have the most important functions and messages included and therefore have a lower memory consumption. This is necessary to increase the number of the measuring points from 24 to 48. The function group busbar with the protection algorithm is completely the same as for the other solutions. This is a very important point. The communication between the bay units and the central units is also based on IEC 61850. In the IEC 61850 system configurator, the assignment of the physical measuring points of the merging units to the central units in the sampled measured value view must be done. For this purpose, a script is provided which automatically performs the assignment according to the specifications from the single line diagram. The engineering effort is therefore significantly lower than with the IEC 61850 compliance solution. With the 7SS85CU solution, a setup with up to 48 measuring points and 6 bus zones is possible. Also, in the 7SS85CU solution, every Sipotec 5 device can be used as a merging unit. The requirement to the device hardware of the 7SS85 is to have an Ethernet BD module for 16 measuring points each. With 3 modules, one comes then to 3 times 16 measuring points, which are altogether possible. Here it is important to know that with the option with 60 measuring points per module will be possible from version 9.40. Until now it was 15 measuring points per module. You can learn more about the 7SS85CU solution in our last tutorial next year. Okay. In the next 2 slides I want to compare our Sipotec 4 solution 7SS52 with the Sipotec 5 solution 7SS85. In the system family, the 7SS85 is fully integrated in the Sipotec 5 platform. With the 7SS52, the central unit is a Sipotec 4 front end, special designed for busbar protection. The bay unit is a Sipotec 3 device. The topology in the 7SS85 can be a centralized setup, distributed setup, or even a mix of both variants. With the 7SS52, it is always a distributed setup. If we compare the communication redundancy, we can offer with Sipotec 5 redundancy protocols like PRP or HSR. But you can of course also use star mode without any redundancy. With the 7SS52, the bay units are always connected via star mode to the central unit. One too fast. The time synchronization is in Sipotec 4 done by the protocol. In Sipotec 5 you can use since version 9.20 the integrated grandmaster clock. No additional equipment is needed in both cases. Here we go. The requirements for the current transformers are the same for both devices. So for the minimum saturation free time we need a value greater 2 milliseconds, a transient dimensioning factor KTD of 0.5 in both times. We will talk about CT dimensioning in the third tutorial. About additional functionality in the 7SS85, we have the really great benefit that you can integrate all the Sipotec 5 platform functionalities to the Sipotec 5 device that you want to use as a merging unit. The typical functions for busbar protection like circuit breaker failure protection and end-fault protection are of course available in Sipotec 4 and Sipotec 5. The protection algorithms are completely the same in both devices. We have the 3 self-adapting algorithms for the differential protection. The 1 out of 1, the 2 out of 2 algorithm, and the algorithm with the filtered measured values. And this is really also a benefit in the Sipotec 5 device, because since we use the same algorithms, we benefit from all the experience with the Sipotec 4 7SS52. If you are already familiar with the Sipotec 4, don't worry, you don't have to learn something new. If you want to learn more about protection algorithms, please join our second tutorial in January. The tripping times of Sipotec 5 are a little bit lower than with Sipotec 4. In the 7SS52, the minimum tripping time for high current internal faults is 15 milliseconds. For lower currents with DC offset, higher tripping times are possible. With the 7SS85, tripping times of 7 milliseconds with the centralized system and 10 milliseconds for the distributed systems are possible. The maximum number of measuring points is 20 for the 7SS85 centralized and hybrid solution, 24 for the distributed IEC 61850 compliant solution, and 48 for the 7SS85 CU solution. For the 7SS52, the maximum number is also 48. The maximum number of bus zones are 6 for the 7SS85 centralized, the IEC 61850 compliant solution, and 20 for the 7SS85 CU solution. Same with the maximum number of couplers. For the 7SS52, up to 12 bus zones and up to 16 couplers are possible. About the safety and supervision functionalities, they stay the same. There is the integrated check zone functionality as an additional trip criterion, and there are comprehensive supervision and control functions like the current sum supervision. The engineering is in both cases based on the graphical engineering in the single line editor. For the configuration and operation, DIXI 4, respectively DIXI 5 is used. For the online monitoring, we can offer for Siprotec 4 and Siprotec 5 the single line based view via display or DIXI 5. There you can check the current values, the differential values for each zone, and the disconnector image with the status of all disconnectors. For the 7SS85, there's additionally the web browser available. The topic cybersecurity is definitely a selling point for the 7SS85. Since the device is a part of the Siprotec 5 family, platform functionalities like role-based access control and IEEE 802.1 based network authentication can be integrated. With the 7SS52, we can only offer basic password security. Another benefit, which is worth to mention here, is that for Siprotec 5, 7SS85, we have the possibility of virtual testing with our Siprotec 5 digital twin solution. It is possible to simulate the centralized and the distributed solution with the digital twin.